finding particular solutions, and equations of curves. Hello, everyone. Welcome to today's lesson. Before we dive into our new topic, let's take a moment to reflect on what we have already covered. In our previous lessons, we focused on the techniques used to find the general solution of a differential equation. Now, while finding that general solution is a vital skill, you'll find that in many real-world practical scenarios, we aren't just looking for a broad, general family of curves. Instead, we are often faced with a specific problem where we need to identify one single, specific curve that satisfies a particular set of given conditions. This brings us to the core of today's lecture, the concept of a particular solution. This is the essential tool we use to move from a general pattern to a precise, unique answer. Let's move on to the next slide to understand exactly what this means. Understanding the concept. Now that we've established that we've already learned how to find general solutions, let's dive deeper into what these solutions actually represent. Think back to when we perform integration on a differential equation. As you know, every time we integrate, we must introduce an arbitrary constant, which we usually denote as capital C. Because this constant C can be any real number you can imagine, the equation we end up with doesn't just represent one single line or curve. Instead, it represents an infinite number of possible curves, all following the same pattern. In mathematics, we refer to this entire collection of curves as the general solution, or more visually, the family of curves. However, as we'll see in the next few slides, we aren't always interested in the entire family. Often, we need to pick out just one specific, unique member from that group. This is what we call a particular solution. So, how do we narrow it down? We do this by assigning a definite, fixed value to that constant C. We find this value by using a specific point, which we denote as x and y, that the curve is required to pass through. In many problems, this specific point is provided to us as a starting requirement, and in the context of differential equations, we formally refer to this given point as the initial condition. Step-by-step procedure to find a particular solution. Now that we understand the difference between a family of curves and a single, specific curve, let's look at the roadmap for how we actually get there. To move from a general solution to a particular solution, you don't need to guess. You simply follow these 5 systematic steps. Step 1. First, you must obtain the general solution. This is the part you've already been practicing. You'll solve the differential equation using whichever method is appropriate for the problem, perhaps using variable separable or homogeneous substitution, until you arrive at an equation that still contains that arbitrary constant, C. Step 2. Once you have that general equation, your next task is to identify the initial condition. Look closely at the problem statement for a given point, which we can call x0, y0, or a specific condition, such as saying y equals y0 when x equals x0. This is the anchor that tells us which specific curve we are interested in. Step 3. Next, we substitute the values. Take those specific numbers from your initial condition, your x0 and your y0, and plug them directly into your general solution. Notice what happens here. By replacing the variables with known numbers, you transform the equation from a general relationship between variables into a simple algebraic equation where C is the only unknown left to find. Step 4. Step 4 is to solve for the constant C. This is pure algebra. You'll perform the necessary operations, like adding, subtracting, or multiplying, to isolate C and find its exact numerical value. Finally, step 5. Write the final equation. This is a crucial step that many students forget. Once you have found the value of C, you must substitute that specific number back into your general solution. This final, completed equation is your particular solution. In the next slide, we are going to walk through a concrete example to see these 5 steps in action. Illustrative example. Now that we have understood the theory behind moving from a general family of curves to a single, specific curve, let's put it into practice with an illustrative example. Take a look at the problem presented here. We are asked to find the particular solution for the differential equation, where the derivative of y with respect to x equals 2x divided by y. We are also given a specific condition. The curve must pass through the point where x equals 2 and y equals 4. Let's walk through the 5-step procedure we discussed in the previous slide. Step 1, we need to find the general solution. To do this, we'll use the method of separation of variables. We'll start by rearranging the equation so that all the y terms are on one side and all the x terms are on the other. This gives us y die equals 2x dx. Next, we integrate both sides of the equation. Integrating y with respect to y gives us 1/2 y squared, and integrating 2x with respect to x gives us x squared plus c. This result, 1/2 y squared equals x squared plus c, is our general solution. As I mentioned earlier, this represents an entire family of hyperbolas. Step 2, now we identify our initial condition. From the problem statement, we know the curve passes through the point 2, 4. This means when x is 2, y must be 4. Step 3, this is where we bridge the gap between the general and the particular. We substitute our known values into our general equation. So, we replace y with 4 and x with 2. This gives us 1/2 of 4 squared equals 2 squared plus c. Step 4, now we simply perform the algebra to solve for our unknown constant. C4 squared is 16, and 16 divided by 2 is 8. On the other side, 2 squared is 4. So, 8 equals 4 plus c. Subtracting 4 from both sides, we find that c equals 4. Step 5, finally, we must write the final equation. A common mistake, which we will revisit in a later slide, is to stop once you find c. Instead, we must substitute this value of 4 back into our general solution. This gives us 1/2 y squared equals x squared plus 4. To make the equation look cleaner, let's multiply the entire equation by 2. This simplifies to y squared equals 2x squared plus 8, or you could write it as y squared minus 2x squared equals 8. This final equation is our particular solution. It is the one, unique curve that satisfies both the original differential equation and the specific point we were given. In the next slide, I'll show you how this exact process is used to solve real-world problems, like predicting how temperature changes over time. Real-world application context. Now that we have mastered the mathematical procedure for finding a particular solution, you might be wondering, why does this actually matter outside of a math classroom? Well, in the fields of physics and engineering, we rarely care about an infinite family of possibilities. We need to determine the exact, precise state of a system at a specific moment. Let's look at a classic example, Newton's law of cooling. This law states that the rate of change of the temperature, which we'll call capital T, of an object is proportional to the difference between its own temperature and the ambient or surrounding temperature, which we'll call capital T sub s. If we were to solve the differential equation for this law, we would arrive at a general solution. This general solution is quite powerful because it provides a universal formula for how any object cools down. However, this formula alone isn't enough to tell us the temperature of a specific cup of coffee at a specific time. To do that, we need an initial condition, specifically, the initial temperature of that coffee at time 0. By using that starting temperature, we can find the particular solution. As you can see, without the particular solution, we would only understand the general pattern or the behavior of cooling, but we wouldn't be able to predict the actual numerical temperature. In the next slide, I'll highlight some common pitfalls to watch out for when you're performing these calculations yourself. Common mistakes to avoid. First, let's talk about stopping at the constant. I have seen many students work through the entire integration process, find the numerical value for c, and then simply stop there. Please remember, the question is asking you to find the solution, which means it wants the full equation of the curve. Finding that c is just a middle step. Once you have found the value of c, you must always substitute it back into your general equation to present your final, particular solution. Second, watch out for incorrect substitution. This sounds simple, but it is a frequent source of error. When you are given an initial condition, like the point we used in our example earlier, you must be extremely careful to substitute the x-coordinate for x and the y-coordinate for y. It is very easy to accidentally swap them when you are working quickly, but swapping these values will result in an entirely incorrect value for your constant. Finally, be mindful of algebraic errors with logarithms. In many differential equations, especially those involving variable separation, your general solution will often involve the natural log of y, written as ln of y. When you substitute your values into these types of equations, you might find that solving for c requires you to use logarithmic properties or even exponentiate both sides of the equation to isolate the variables. Don't let the algebra trip you up. Take your time with these steps. Now, before we wrap up today's lesson, I want to pause and discuss some common pitfalls. Even if you understand the steps we covered in the previous slides, it is very easy to lose marks due to these 3 specific mistakes. Keep these tips in mind, and you will be well on your way to mastering this topic. Let's move on to our final summary of the key takeaways. Key takeaways. To wrap up our lesson today, let's quickly recap the key takeaways to ensure you have a solid grasp of the material. First, remember the general solution. As we discussed earlier, when we integrate a differential equation, we are left with that arbitrary constant. See, this represents a whole family of curves, all sharing the same mathematical pattern but shifted or scaled differently. Next, we have the particular solution. Unlike the general family, this is a single, unique curve. It is the one specific member of that family that is forced to pass through a specific point, which we call the x and y coordinate. This brings us to the initial condition. This is the crucial piece of information we identified in our step-by-step procedure. It is the specific point, or the given values of x and y, that we use to pin down the exact value of our constant, c. Finally, if you ever feel lost during an exam, just remember this simple 4-step process. Start with your general solution, then perform the substitution of the given point, use that to solve for c, and finally, write out your completed particular solution. If you follow this flow, you'll be able to navigate any problem of this type with confidence. Great job today!